Fine. So first question is, how many of you saw the total array ordering webinar? Hands up. Oh, you saw it. Oh, okay. Okay, that's good. So then this is new stuff to you. Fine. That webinar is very, I mean, so it's supposed to be interactive, and but really because of time delay and the awkwardness of it, it becomes very much a presentation. I envisioned, I've basically taken the slides from there and I've modified them a little bit for this, but I hope that we can make this a little bit more interactive. So by all means, jump in, ask questions, point out my errors and so on. And it was Jay that did the main presentation on the webinar. I'll have to play Jay today. Okay, so for a long time, or since I think from the beginning of APL, we have had grade, which can tell you the order things would have to be put in order to be sorted. And it works on simple character in numeric data. So it doesn't sort by itself, but it tells you the positions. It says that the first we want to take number 1, that's the A. Then we want to take number 3, that's the L. Then we take number 2, that's the P, in order for this character vector to become sorted. That's what grade does. And so these are the correspondences, of course. Now, I said this was a character vector, and we were grading the individual characters in the character vectors. What really is going on is that grade looks at the major cells. So what are the major cells of an array? For a vector, the major cells are the scalars, individual characters if it's all a character array. If it's a matrix, then the major cells are the rows. If it is a 3D array, then the major cells are the layers, and this continues. So it's what corresponds to the first element of the shape, and they can then be reordered. So here's an example of that. This is a 5-row character matrix, simple matrix. The display form I'll be using here is the display form you'll get if you turn boxing on and you set the level to mid. That both gives you a somewhat dense display, but it also gives you these indicators of X's, and also if it also indicates data type. So in this case, in the very bottom of the frame, it's just a smooth frame. It means it's a simple character array. But if it was numeric, it would have a tilde. If it was nested, then it would have an epsilon and so on. But that's important here because we need to see exactly what's going on. So here's an example. Here's our character matrix, and then we can grade this matrix, and it tells us these indices, and then of course it says that in order for this character matrix to be sorted, we need to take number 3 first, and then number 5, and so on. And we're not done sorting, of course, but we can just take these indices and we use them to index into the original data, and now we have proper sorting of our character matrix. We can write this in different ways. There's a benefit to writing it in this way, both because we don't have to worry about how many dimensions there are. The index primitive works on major cells if you just give it an enclosed simple vector. And so we can see up here, because we had a matrix, we have to elide indices in the second dimension, and we don't have to do that for index. So we don't have to worry about what kind of data we're dealing with. It just works. And indeed, in version 17, we have made this an idiom, which means that the interpreter will recognize this as a single unit, parse it as a single unit, doesn't spend any overhead time to figure out what's going on here, and it just sorry, just select the best approach to sorting your data. It just goes straight ahead and sort it, not looking at what's actually written inside. So it's very fast. It works on any dimensional array. So that's another benefit of using this one. So that's what we're going to use. Same good thing goes for descending sort. It's also in version 17 made into an idiom, and it's fast. So we're going to take this and we're going to assign it. So whenever you sort, that's what I'll be using. But of course, you can write it in any number of ways, whichever one is your favorite. So we apply that to Matt, and we get the sorted matrix as we would expect. Now, you guys are all APL experts, but still you might have bumped into this vector of text vectors, and then you try to sort it, and you get a domain error. That's how it was. Yeah, exactly, right? Hands up, who hasn't done that? Everybody did that. Okay. Well, or in version 16, it gives a domain error. That's how it is. In version 17, it sorts it. So, yeah, it just works. So that's really the main gist of this. I mean, I'll be talking a lot about all the details and so on. But the main takeaway from this is that in version 17 on, just sort your data and grade your data. It'll just work. It'll just do what you expect it to do. If it doesn't, then well, get back to us. So let's look at more at how grade traditionally has been grading things. So consider this. This is a kind of imagined representation of a 2-row matrix. So the major cells are character vectors, and they have the same length. There's really a blank at the end of Roger here, and that's how it has to be because higher rank arrays are orthogonal in Dyalog, well, in any APL really, and that means everything has straight edges. You can't have ragged arrays. You can't have a matrix where each row has a different length. For that, you have to have a vector of vectors instead. So the way that it really works for any array, you could split it up like this. You can look at the pieces of it, and you can combine them. So let's say we have these 2 character vectors. You can put them into a higher dimensional array, and then you can grade them. So that's how we'd have to deal with character vectors in the past. And so then grade tells us, of course, that A comes before B. If B had come before A, then the grade would have been 2-1 instead. And so now I'll introduce some notation for that. This is not an APL primitive, and it cannot be an APL primitive. It doesn't follow APL syntax. It's just a notation I'll use for now. It's red to remind you that it's not APL. What it means is precedes, and there are corresponding symbols that precedes or identical to or succeeds, follows. So this means that the character vector Morton precedes the character vector Roger with a blank at the end. But that's how it has been until now. We want to be able to take any array whatsoever, not just simple character arrays or simple numeric arrays, and ask this question: does this array precede some other array? And that defines an ordering between them. If we have an ordering between them, then we can define grade in terms of that. So grade can figure out what is the order you have to put this in so that they come in their sorted order. For that, we have to be very careful to define an exact ordering, so that for any 2 arrays that are not identical to each other, there's an answer to this question: does this array precede this array? And it might sound trivial to do that, but imagine you had an array like this. It's a big mess. So it's a 4-element vector. Well, it has an uneven depth, right? It's going to have a negative depth because it's uneven, and even the elements have different rank and so on. There's obviously nothing wrong with it. You're allowed to use it, but imagine if you wanted to grade this, sort this, then you have these 4 elements, and we need to decide their order. Eventually, you end up having to ask this question: does 0 precede a 2x3 matrix of characters. Yeah, yeah. Well, of course, right? That's. Wish it was that easy. Right. So we have to have rules to cover all the cases. Until now, it was very simple. You know, we know what the order of the alphabet is, basically. I mean, it's Unicode order or classic quad-AB order, and we know what the order of numbers is. We just look at the or what the value is, and that's it. But now we have to be able to compare anything with anything, any rank, any depth, any data type. And so that's what this is all about, the total array ordering. And from total array ordering, we got the abbreviation TAO. From there, we went way out there in the forest and Eastern philosophy and whatever not. But the name total array ordering, or TAO, it comes from total order. Total order is a known concept in, I guess, mathematics or in set theory, ordered set theory. There isn't really a fixed notation for how to write it. Here they use a normal less than or equal to, but really what's going on here is precedes or identical to. And Wikipedia goes on and on about this. But that's where the name comes from. And specifically what we're talking about is total order of the set of arrays. And so that's why we have the name total array ordering. It isn't quite total because Dyalog arrays can have refs in them and other nasty stuff, and you can have circular refs, and it gets really complicated what comes before what when it refers to itself inside, and it go on forever. So it isn't all arrays. It's almost all arrays. It's all those arrays that it's meaningful to sort. We may be able to extend it in the future with more stuff, but for now we've stayed with what's sane. So let's go into the rules about how do we decide we have these two arrays, which one precedes which. We start out with some restrictions. Remember, we already have grade, and grade looks at the major cells. It has to stay that way, and it also means that as long as we have a simple homogeneous array, grade of course needs to keep the behavior it currently has. So whatever it is we decide how to do all these crazy mix and matches between data types and structures and so on, still when we try to apply it to something that already works today, of course it has to still give the same result. We don't want to break anything. All this stuff is all additive. The only thing we've changed is a domain error has ceased to be a domain error, and you get a meaningful result instead. We also want to be consistent. What that means is that you can read about it more on Wikipedia under the total ordering. What it tries to say here is that we define an ordering between two different members of the set. In our case, it's a set of APL arrays. And if one precedes or is identical to other, or the other one also, so you do the reverse also, the second one precedes or is identical to the first one, then it comes out that they are identical. We can't have inconsistencies where we grade two different arrays, and depending on the order they appear in, then grade will respond that they have to be in a different order also. It's a strict rule set, consistent rule set, that there is an ordering between all different arrays. And for that, we need to have this concept of equality. And so while this part, the precedes part, is the one we're trying to define, this part, the identical to part, for the members of our set, the set of APL arrays, is already defined because we already have a match primitive. So whatever we do, we have to be consistent with match. It might seem obvious, if they're the same, they're the same. But when we look at the contents of arrays, it's not always so obvious, because from match you also have, of course, match, or not identical to, and it's not so obvious that these two empty vectors are different. One is numeric and one is character, but there are no numbers and there are no characters in there. We have to keep that in mind. In order for us to be consistent with match, we have to be consistent with match, and that's what has to define our ordering. So that's important. We'll come back to empty arrays later. It's complicated. Right, so going through these rules from simple, easy to understand, obvious rules, possibly, to the more complex ones. We'll start off with just comparing simple scalars, and then we can build up comparison of arrays that are made up of these scalars later. So occasionally you can end up comparing a character to a character. And luckily, that's a solved problem. We already know how to do that. Look at the Unicode order or the Quad-IV order for classic. Then it has to stay that way. Remember, we have to be consistent with what we have already. So moving on. We have real numbers, right? We already have the smaller than primitive. That will tell us whether one number is smaller than another one. That just works. But that's only works for real numbers. What do we do with complex numbers? Well, it's kind of axiomatic. You can't define an ordering of complex numbers so that all the mathematical rules about comparisons apply. Thank you. So what we've done is that we kind of look at the field of complex numbers and flatten it out. So it's a two-dimensional field. We can look at it as we have a real axis. So we have the numbers -3, -2, -1, 0, 1, 2, 3, and then we have the imaginary part going vertically. And so what we've done is we've straightened them out in ordering like this. So in between -3 and -2 are all those numbers that are -3 plus some imaginary part. And then we get all the way to -2, and then between -2 and -1 are all those things that are -2 plus some imaginary part. And then the same thing goes the other direction. Just before -1, we have all the -1 minus some imaginary part, and then continues over on the positive side. So we got here 1, and then 1j1, and then 2j -1s. We're approaching from the other side, and then eventually 2. And this gives us a consistent ordering. It's not a mathematical ordering. You still can't say, and we have not extended, and we can't extend less than and its family members to apply to complex numbers. It is not less than, but it does precede. That's the difference. And that's why we use this symbol. So this is how we've ordered the complex numbers. It could have been done kind of like the transpose of that. We could have gone the other direction. But this seemed like a more obvious solution. And I think the one other programming language that has something similar is Mathematica. They went to the exact the same thing, which we only discovered afterwards. So that's nice. Then we have numbers versus characters. Is x greater than or equal to 42? It's just a decision you have to make. There's nothing intrinsic in this that makes it so. We settled on numbers before characters. So all numbers are on the left side, if you can say that, or all numbers precede all characters, no matter what they're. Mistake or? In the beginning, wait, isn't that the new stuff? That's the new stuff. That's the new stuff. I don't subscribe to the new stuff. That's it. I mean, this was a major it was a discussion back and forth. What should it be? It also seems that other languages, other systems that allow you to compare numbers to characters have gone with the same approach. But I should say, I mean, we have come to what I think is a really, really good system. Out there are programming languages and systems where that appear to have some kind of total ordering where you can compare anything to anything, and then you look into it, and turns out that it's really arbitrary or it's completely crazy. I mean, it's interesting. Like I noticed in Python 2 allows you to compare anything or anything. Python 3 they took that away. And I think that was a good decision for them to take it away, because the reason something comes before something else in Python 2 is that it compares the English name of the data type alphabetically. Right. So is it a number? Is it a float? Or is it, wait, have to, and the same thing goes, yeah, the other languages do other interesting things. Turns out in JavaScript, if you compare numbers to characters, it, without telling you anything about it, it will convert the number to a string and then compare. So that means that it looks at the characters 1, 0, 0 compared to, so that means that A comes after 100, but space comes before 100, and 10 comes before 2.
It's all dependent on your formatting.
Well, there's JavaScript's formatting rules, right? But they're consistent. But 10 comes before 2 because 1 comes before 2, right? So, what was it? K sorts, how does it go? K sorts all integers before all floats. Just keep that in mind. That's so the correct ordering is 1. How does it go? 1, 0.5, 1.5. Right? That's okay. So we settled on this, and Mathematica also decides on that numbers go before characters, and Excel also does this. But yeah, it seems to give us the results that we want most often. And then we added last minute one more thing, and that is quad null. Quad null is it's something you really shouldn't have in APL normally, but if you interact with the world outside, like with .NET, then you can get in these nulls as placeholders for it. It basically means there's no data here. And so it was a principle we'll come back to later, that nothing comes before something. We also settled on that the scalar that represents nothing comes before anything that's something, even the smallest negative number. So so the whole ordering is that first we have null, and then we had this straightened out field of complex numbers, and then characters in the other end. This is our this is the ordering from first to last. Okay, so that was for simple scalars. That means we can use this now by looking at larger arrays. We can drill into them until we are only comparing scalars, and then we can make decisions based on that. That will help us in most cases. So now let's look at arrays that are not scalar, larger arrays. But for now, we're limiting it to arrays that have the same shape. So for example, here are two 4-element vectors. And the way we do it here is that we compare them scalar by scalar from the beginning in Ravel order. So that means we look at J versus J, and they're the same. So we proceed to the next character or next scalar. It could have been anything because we know now the ordering of scalars. And then we have an A versus an O, and we have a decision that the name J comes before the name John. But notice again, there's a blank here at the end because they have the same shape. Had to have the same shape. We still haven't established the rules for grading things that are comparing things that have different shape. Same thing goes for more intricate arrays. So here we have nested arrays. And we do by exactly the same approach. We step into them element by element, one step in. And again, when we have the first element, but the first element again is not a simple scalar, so we still can't apply our simple scalar rules. So we step in one more step into that. And now we have simple scalars that we can compare. And again, we go element by element until we find that D comes before F. Then we have our ordering set. Right, that's all very good for things that have the same shape. But what if they have different shapes? So you go element by element, and eventually you run out of elements to compare. There's nothing there. So you can have like a word list of this. Some of them have a shorter length, some of them have a longer length. What are we going to do about that? So we had a discussion and settled on something called lexicographical order. And if you're interested in reading material, Wikipedia goes on and on about this. It's not simple, I can tell you that. And they only talk about simple strings, right? We're talking about multidimensional arrays with all kinds of stuff inside. So this was a lot of work. But here we are, 400 and something emails later, and I think we have a good solution to it. So consider here, for example, car and carpenter have different length. Lexicographical ordering specifies that nothing comes before something. That's at least one way of saying it. So another way of saying it is that if you have two strings where one is a prefix of the other, as here car and carpenter, then the prefix comes first, and the continuation string, the one that has a continuation, comes afterwards. So CAR, and then we look at whether there's anything after that. And so we see that CAR has nothing, and carpenter has something, penter, and nothing comes before something. So therefore, car comes before carpenter. Make sense so far? Okay, so we can, of course, apply that to anything. Another way of saying it is that the shape is more important than the content. First, we look at wherever we have the same thing. So we're going through it here until the second character, and then we can eliminate N and T out of the picture, and then we have CAR. So far, all the content is the same, and at this point, which really is at every point, we look at what is the length. So this one ends here, and the other ones continue. The one that ends here comes before the ones that continue. So the shape is more important than the content that's there. Doesn't matter that it's a P or a -100 or whatever it is, because it's beyond the shape. We don't care. It's something. So one way we could have done this is to mix the two. So the mixed primitive will pad with prototype element, and so you get car extended with spaces, and that's all very nice, and they all sort quite well. But imagine if you had, for example, car followed by space and car without a space. Clearly, they're not identical to each other. Remember our consistency rules. We stated that if two arrays do not match with our primitive that does already tell us whether something matches or not, then we cannot order them the same. And if we were to pad with prototypes like this, then we would end up adding, as long as we have carpenter being very long, we end up padding car with some spaces and car space with one less space than that, and now they're not distinguishable anymore. So this fails on our requirement to be consistent. That's one problem. Another problem is that space isn't the first character in the character set, neither in classic QuadAV, nor is it in Unicode. It's number 32. And that means that if your character vector, in this case, but of course it could be anything, contains any character that comes before space, of which there are 31, then you end up having something that is longer, something where you have something coming before another array where there is nothing, and that breaks our rule of lexicographical ordering that nothing must come before something. So this is not a solution. It doesn't give you the right result. You compare them, then you get the opposite grading of what you want, and you get unhappy. It might not seem so bad for character arrays, but we also wanted this to work on all types of data. So, for example, here 1, 2, 3 compared to 1, 2, 3, 4, we want 1, 2, 3 to come before 1, 2, 3, 4 because it's lexicographic ordering. A prefix comes first. Nothing up here in the corner comes before something. That's all very nice. If you mix them, you fill in a 0, you compare them, 0 comes before 4, nice and dandy. But what if they're negative? Right? So now, if you were to look at them, so we have one prefix and another, that means -1, -2, -3 has to come before -1, -2, -3, -4. But if we mix them, we get a 0 in the corner. And we all know that -4 comes before 0. So grading that gives us 2, 1, and that's wrong. You don't want that. So scrap that. We can't do that. We have to come up with a different solution. We came up with this. This is the owl. It's very wise. This is not a character. It is. We're going to speak about it as if it is a scalar, but it is not really a scalar. It is a placeholder. It's a fill. It's a fill first, not fill last. It's a composite symbol that we made up here. It's not in Unicode even. You can never type this. We'll never be able to type this. We composed it of infinity and negative to give you the sense that it is something that's as a negative infinity kind of thing. It comes before everything else. And we use this as a scaffolding to define our rules. So we were going to deal with this element. Whenever you see this, remember it comes before everything. It's not a scalar because it comes before even an empty array, right? So, and that would break the rule of nothing before something. An empty vector should come before a full vector. This is something that universally comes before everything else. And so we add that to our ordering of things. It comes before everything, even before null, even before empty arrays. And now, if we use this to pad with, instead of just using mix that uses prototypes, then we can fill up the shorter vector to have the same length as the longer vector. And then we can go element by element. So we have a prefix until there, they're the same. And the next step is comparing this fill first element with a P. And we know the fill first comes before everything else, including P. And we're done. So this solves our problem that nothing, it's in a way a placeholder for nothing. It represents nothing. There's nothingness in each of these positions. And nothing comes before something. And we can also use this for higher rank arrays, even though there are multiple dimensions in which we need to pad. So here's a 3-2 and a 2-3 character numeric matrix. And so we pad them out until they have the common maximum shape. So now they're both 3 by 3. And then we proceed as we have always done. Now we are having two arrays of the same shape, which means we could use this lamination thing and grading, but what really is going to happen is that we go element by element. So 1, 2, and then for the third step, we're comparing fill first with 3, and of course nothing comes before something, and we're done. We decided which one comes before which. That's it. Have a solution. Now that's all very nice when they have different shape but the same rank, so we can fill them up to have the same shape. What if we have different rank? So you have a character vector compared to a matrix. What are we going to do? So what we found was that we can amend the shapes until they get the same rank. So we do that by putting ones on the left of the shape. We'll get back to why that's the right side to put them on, left side to put them on. But for now, we extend the character vector so it becomes a character matrix. Now they have the same rank. And then we go back to our previous rules. You have two different arrays of same rank but different shape. So we pad up until they have the common maximum shape. And then we go element by element until we find nothing before something, and we're done. So it can happen. What? Yes.
In the previous slide, you don't need actually the padding.
We do need the padding because, well, in this case, in this particular case, you don't need the padding because you're done as soon as you are with the second element. We only know that because we now can compare them. If it had said Adám on the left, then it would eventually have ended up comparing the nothing to something. So we do need the rule. What can happen occasionally is that you have two arrays where match will tell you that they are indeed different from each other, and they have different rank indeed. And so then we up the rank of the lower rank one, and now they're identical. So now what do? This doesn't, there's nothing here to compare. We could go through element by element and there's nothing there. So then we backtrack. and we look at the rank instead, and we use the rank as a tiebreaker. So this gives us that, you know, simpler arrays, lesser ranked arrays come before the otherwise identical brethren that have a higher rank, and that's our tiebreaker. So I mentioned that we put ones on the left of the shape, and there are a couple of reasons for doing that. One of them, we phrase it as visual fidelity. You may have noticed that if you put more ones on the left of the shape of any array, the display form in the session will be identical, as long as you don't have boxing on, at least. Actually, even if you have boxing on, it will also do that on the lower levels of boxing. So a scalar character looks exactly like a 1-element vector, and a 3-element character vector looks exactly like a 1x3 character matrix. Same thing goes for numeric things. When they get printed out, you can't actually tell the difference between them. And so because there's something that look very similar, then imagine you had your big phone book or big dictionary of all APL arrays, and you're looking up APL arrays there. You would expect that arrays that look exactly identical to each other would be listed in your dictionary of all APL arrays very close to each other. So by doing it in this way, we get that desired result, that arrays that are similar looking to each other would be listed next to each other. And the alternative would be putting ones on the right, but that would mean that a character vector would sort very similarly to a column vector, and they indeed look very different from each other. There would be 3x1 going down. So we found that it made the most sense to pad ones on the left for the purposes of this. Okay, so these are the basic rules. It's just a little bit more to go. Simple scalars, nulls, numbers, characters. When they have the same shape, we go element by element. And if they have different shape, then we pad them up so they have the same shape. And if they have different rank, then we pad the rank on the left with ones. But if you were to try to preempt the interpreter to figure out what is it going to answer, you're given these two arrays, then it might be an idea to go from the bottom up instead. So, you first say, okay, do they have different rank? Pad them if necessary. Do they have different shape? Pad if necessary. Do they have same shape? Go element by element, and then when you meet two scalars, you use the rules for simple scalars. Go up like this. Just one more thing, empty arrays. You might think that we could just take these, we thought that we could just take these rules and just apply them to empty arrays, and then it came and bit us when we found an example of the opposite. Consider these two. Empty arrays. We all APLs, we're all comfortable with this. 200 row Zilde, or any numbers, is empty. And 003. So let's remember the rules, right? We look at the maximum shapes and we pad them up. Now we get 203, right? And what's the next thing? Oh, now they have the same shape and the same rank. So now we go element by element. Wait a minute, there are no elements. So how are we going to decide here?
Numbers, characters.
Ah, right, but the shape is also different, remember? The original shape. There are two differences between these two arrays. One is the data type. The other one is the shape. So backtrack, this system doesn't work, but we have to make that decision. Are we going to go by the prototypical items, which remember they aren't there, or should we go by the original shape before we try to extend them? And if you remember, I said much earlier that shape, say this.
Shape is a tiebreaker.
Yeah, shape is typing. What prototypical item is also tiebreaker. What we went with, it was a discussion back and forth. What we went with was that we go by the content first and the shape last. Then again, please call me if you ever you happen on a real world example where this is going to matter for you. I still haven't seen any. And then, of course, if both of them have the same data type, then we have to tiebreak using the shape. So that's how it will work. And those are really all the rules. So the very last thing is if they're both empty, then we compare the type, then we compare the shape, and we're all done. what does it apply to? Grade up, grade down, and the new primitive from 16 iota underbar, dyadic one, which is interval index. Because interval index takes a sorted, has to be sorted left argument, and then it looks at every element on, or every major cell really, in the right argument, and it tells you where in the left argument does it fit into sort order. So clearly it has to be able to determine where in the left does this fit in, which ones does it precede and which ones precede it. So this is what it applies to. Okay, let's see it in action instead. Right. This is a matrix of Turing Award winners until 82. The funny line across is I have a setting set so that we never end up with a spelling session, which you can set that with a rows user command. Just abbreviate it. And you can see it is a rather complicated matrix really, because it has the left column consists of character vectors, and the right column consists of numeric scalars. So it is uneven in its nesting level, and it is inconsistent in its data type. So of course, old grade couldn't deal with this at all, and it wouldn't even help to mix it, because you have it's not homogeneous in data type. You can see that here. It's important to keep track of that later. It's numeric. That's the tilde down here. These are character, and you can see down here that these are vectors, and this one is a scalar. Doesn't have an indicator there. So let's define our sort. And you see that the interpreter colors is yellow. You can turn this option on to show idioms. So this colors is yellow right away based on my settings to show me that this is an idiom. It's going to run fast. I didn't type anything wrong. And now we can sort our Turing Award winners, and it just works. It's sorted, and then of course we compare the major cells. So those are rows. We compare the rows to each other, and we go element by element. That means we look at the name first, and then we go dig into that, and we compare element by element of the name. So we can see here C, D, F. It's in alphabetical order. But let's say that we wanted to write some history about these, and it's going to be a major work. We're going to have to split it into multiple volumes, and we want to write on the back of each volume. You're going to write that these are all the Turing Award winners from A to K and so on. So we need to split them up. So let's decide on some. Is it big enough? Everybody see? Yeah. Okay. On some volume cutoffs. So I find that these are some good cutoffs. So we're going to have all the Turing Award winners that begin with from A up until before F, and from F up until before K, and from K up until before P, and the last volume is going to be U and to the end of the alphabet. So we're going to categorize them, and for that we're going to use this iota underbar. So we're going to look at each entry in our table of Turing Award winners, and we're going to use this interval index to look at where would they fit in between this A and F and K and P and U. That tells us which volume does it go in. In fact, it's a little bit more complicated than that, because if we try applying it, so we're categorizing the Turing Award winners here. So you can see it actually gave me a matrix, and that's because it's comparing each element in our list. So it takes the name and then the number, and so it says we get a 0 here. It's trying to tell us that numbers come before everything in the alphabet. That's our rule about numbers come before characters. But it doesn't matter, because what we're interested in is the first element. So that's the left column. So this tells us for each name which volume they're going to go in. So now we can define a function which chops our data into the appropriate pieces. And for that, we're going to use the key operator with a left argument. So what this is going to do is it's going to say we have our raw data on the right, and we have the on the left we have the categories for each one corresponding to each one of these entries, these winners, and the result is just going to be the enclosed. We're just going to glub them all together. All those that have a certain category, they get glubbed together. The ones with the next category, they get glubbed together. That's what key does when you use it dialectically. So now we can use chop on our string of winners, and here you go. Here are our 5 volumes of that we need to write. But notice, of course, the key deals with everything that comes in the order that appears. So we can see that we have the ones that are P or PRS there in the volume on the left, and the first volume really is here on the right. So internally in each volume, we still have the original sorting by year, which is probably reasonable to have. But our volumes are not in the proper sorted order. But remember that we can sort anything, including this very nested complex array. And here you go, ready to start writing. Just works.
That's cool.
Good.
I like that.
It's supposed to be. And let's do another one. Some of the people over here on the other side of this, they will like this one. More than 400, yeah. Gmail has this thing about capping conversation threads at 100 emails, and it starts a new thread with the same subject line. So we're just counting chops how many times. So we're currently on the 4th stack of 100 emails for this. Yeah. Well, we've been working on this.
He's talking about it using J. Turned out to be not quite that.
Yeah, no, it doesn't work. Yeah, I didn't mention that, but J claims to have a total array ordering, and it in fact isn't. So J also has a match primitive like APL, and it is possible to find intricate J arrays where match will tell you that they are different, and your own logic also will tell you that they're different, but grade in J will treat them as if they're identical. So J actually fails at doing total ordering there. It is not easy because the people who made J are very clever.
What did Bubba say about it?
I think they logged a bug report or something. I don't know if they can fix it at this point. It's been there for a while, but they were not aware of that. Right, let's deal with some stocks. Does this look familiar to anybody? This kind of thing. So this is a matrix of stock IDs and the time step when we got the quote and the value and how many we have and so on. Doesn't really matter what it is. I'm going to define an operator that we may add to APL in the near future. At least I hope so, because I find it really useful. Might have heard about it. Under or dual, it exists in J already. It's a slightly simplified version of it. Yeah, I know. That's why we needed to have it predefined for you. It might look like an awful lot of Greek, but what it does is it takes 2 functions and it just applies the left function after having put the argument under the influence of the right function, using the left argument if there is any. And then when it's done, it undoes this. So you can have, similar to a lot of things that goes on in the world. If you ever took a beer out of the refrigerator, you will have noticed that you have to open the door first to the refrigerator. So you're taking the beer under the influence of opening the door. And then when you're done, you do the opposite action of closing the door.
Never noticed.
You never noticed. Now you noticed. Now you'll be so self-aware. Next time you take a beer out, then you'll be much more aware of what you're doing. Also, if you take a lot of beers out, you might forget that to close the door. So, but a lot, if you're aware of this, you actually notice it in a lot of applications, a lot of places. We have this kind of algorithm. You have to mangle the data in some way to make it palatable to your algorithm, and then you do whatever you need to do with it, and then you have to undo everything to put it back in. Another example would be, let's say we use APL for data processing. I get some web data in that comes in as JSON. I convert it from JSON to an APL array. I do all my APL magic, and then I convert it back again to JSON. That would be doing my APL under JSON, right? Under converting from JSON, convert it back again. So there's a lot of things like that you could do. So this is a useful operator. This is a simplified version. There's more that could be done to it, but it's enough for what we want for now. So of course we can sort. Same thing as before. We can sort our stocks. And of course it's going to sort element by element, which means we're sorting it by symbol. That's what it's called, right? Alphabetically. And then if there are duplicates, we go by timestamp and so on towards the right. But maybe I don't want to do that. I want to sort by the second column instead. So there are different ways I could do this. I could just use bracket indexing, but here's a cool little way to do it, and we'll see later that it gives us some symmetry. So if you say sort under the one rotate. So one rotate is going to take the symbol and put it all the way over on the right, and then we sort, and then we rotate back again the other way. Right? So that means we're sorting by all the numeric data. We don't actually care about the symbol. We want the information there, and it just works. So now we have sorted here by the timestamp, and then we can say, look at this. Okay, what's going on here? We're going to select the second major cell under transpose. This might seem like an excessive way. I'm sure you can come up with an easier way to do this, but you'll see a symmetry because of this later. So this is pretty neat. This gives us our timestamps. What happened here? Major cells of a matrix are the rows, but we don't want to select a particular row. We want to select a particular column. So we flip the matrix over, we transpose, then we select this, and then transpose it back, and then transpose is not going to do anything at that point, because transposing a vector doesn't do anything. But this gives us our vector of timestamps. And the reason I did that is because I want to speak about that a little bit. This is called the ISO 8601 timestamp format, and it is chosen very carefully. It's very strict, so that you can do a naive text sorting on it, as if it was just a normal text string, and still get a proper sorting of dates and times in their order. And the reason they did this is because it's a little bit complicated to sort timestamps, and which are really vectors of numeric data. But we'll get back to that. We'll see that if we grade that, yeah, then and then we'll later compare that to grading the actual numeric data that's in there, not just looking at them as strings. So that's why I did this slightly awkward way of getting them out. You'll see in a moment.
But you like that because it was a purely functional expression
That also, but I wouldn't write that normally. You'll see in a moment why I did it. So because it comes really neat later. So let's try to convert this timestamp to some numeric data. As you can see, there are actually exactly 7 pieces of numeric information in here, which are exactly the 7 elements of QuadTS. So we actually have the QuadTS in there. So let's convert these to QuadTS. There are different ways you could do it. One neat way to do it, I think, is we define a little function that looks at whether things are punctuation. They're punctuation if they are not digits. So now we can say, let's take the first one of these. That's this one, and then okay, look at that. So this gives us the Boolean whether they are punctuation or not. And now we can say that we take spaces and we put them at those locations that are punctuation. Now it's beginning to look recognizable. The only thing we're missing here is executing it. Now we get a numeric vector that is the quad-TS version of that. So we can take this function and give it a name, and then we apply. We could take this stuff we had before.
What is that expression for the
Well, quad-VFI will not let you do this easily because you don't have spaces in here. You have various characters, so you'd have to give it a left argument. But even then, the period is likely to give you a problem there, right? Yeah, you can set period, but it's you're playing with fire here because you have something, a decimal point, which is a separator. It looks like a number. It could work. Yes. But you have to have the entire list of characters that are separator, which are all the other characters than digits. So you have to do with an entire Unicode range without quad D, right? But if you know the format, yeah, this one is more general. You can use it for finding. But yeah, sure. That's not the point of it here. So here we have them, and this is my point. That now this old expression gives us the grade of the character vectors, and here we have the grade of the corresponding numeric vectors. And so we can see that with our total array ordering, we have managed to get something that also solves that problem that ISO was dealing with, and therefore I had to define this kind of hard to read for humans format, that awkward T in there. So wanted to show that. And now for why I chose a strange way of getting this information out, and that's because there's a symmetry between the index primitive and the at operator. So for this, just selects the second row. At also works on major cells. So if we replace the index with an at, which goes on the other side because it's an operator, now we can apply this nums to each one, and here we go. Now we have applied this converter function to each cell in the second column. So that's why I didn't use square brackets, because then we couldn't do this. So this is at under transpose, and then of course we can go and grade that, and we can try to not do it, and see that the same system worked. Right. Are we doing on time? Okay, just keep going. More examples. What? What is it?
Copy and paste.
Take a break. Okay. Any questions so far? No, nothing. Okay. Right. So in the webinar, I demonstrated something called natural sorting, and I showed how we could sort differently than what JavaScript does. When you have embedded numbers inside character data, we don't want to sort digit by digit in the alphabetical order. We want to sort them as proper numbers. Then I got a question from one of the people in the audience. Hey, but what do you do if you have not just simple integers? You have negative numbers and decimal numbers and whatever not. It could be anything. So how are you going to deal with that? So let's try that.
Yeah, I wonder what tie ordering would look like.
Tie ordering?
Like
Oh, yeah. Okay, so here are some names. You see them? Blow up a little bit. Okay, we are going to attempt to sort this. But we don't want to sort them character by character. We want to sort the embedded numbers as numbers. And you'll notice there's some stuff going on here. We have complex numbers. But remember, we can grade complex numbers. We have numbers in exponential format, a little bit of everything. We even have some things to throw us off. 1e, 10j. Those should sort as just a 10. I've tried to make it as bad as possible. How many of you have used regular expressions? Okay, so you should be fairly familiar. If you want me to, I can go through whether I'm going to use a regular expression here. I can explain it to you if you want. I'll show it to you, and then how many of you have used a regular expression that after you write them, you can't read them anymore? Okay, so you're somewhat familiar with that.
Also
Good.
written APL lines like that.
Oh. Okay, so here's a regular expression. Okay, everybody understands? No. Okay, this is not APL. This is what I came up with on the train on the way here. This, in a sense, defines what an APL number is, and what it's saying here. I'll go through it. So I know it looks crazy, but what I'm saying here is these parentheses, they indicate groups that we can then refer to later or deal with as a whole. We'll get back to that. But we start off over here. A number begins with an optional negative sign. Then it has one or more digits. So that's what this means. Is a \d is digits, and plus means one or more of them. Then we have a period, which is optional. And then after the period, we have 0 or more. That means it's optional. More digits. Or another way of that you can have a number is you have, again, an optional negative sign. Then you have 0 or more digits. Then you have a period. And then you have more digits. And that's so that you can handle things like 0.5, meaning 0.5. And then optionally, so this entire parenthesis has a question mark after it. That means optionally, you have an E following that. And then again, optional negative sign, and then just one or more digits, which is because you can only have an integer exponential format. And then you can optionally, again, at the end, so that's why we have the question mark at the end, have a J. And then this means group number 1. So that's this part. So we have the same pattern, just a shorthand to have the same pattern again. Of course, with the complex numbers, you can have the same thing on the left side of the J as on the right side of the J. So this specifies with a regular expression what a number is. So we're going to use that. We're going to specify a function, so we can use quad R and quad S can take a function right operand that will get called on every match, anything it finds that matches a pattern. And I'll explain it in a moment what it's doing. But we're going to have a guard that is just a boolean that just tells us whether we should do anything or not. So what we're saying is if pattern num will be a 0, if pattern num will be a 1, then it will indicate that what we found was not a number, and so we just leave it the way it is. We leave the match the way it is, and let's go back to a more font size here. But if pattern num is a 0, that will indicate that it is a number, and so then we're going to convert it to a number by executing it. So we'll try that in a moment. Now we're going to define an order, which is going to be a grade of some data that we have pre-processed for our purposes. What we're going to do is we're going to use this pattern for numbers and capture anything that looks like a number, but we're also going to capture anything that doesn't look like a number. So that just means any character. So we're using quad S. Quad S will first look for, in every position of the input, it will look for anything that looks like a number. And then if it's not a number, it will look for anything, and it will, of course, match anything. And on every time we find a match in any of these two capturing groups, capturing patterns, we are going to use this function execnums. And so this is where pattern num comes in. So pattern num 0 is num, and pattern num 1 is the anything. And though that's why we say if it's 0, we don't do this. We go over here, we execute it. That means it was a number. And otherwise, if it's a 1, that's this one. Then we just leave it the way it is. And then that's going to chop up our input in lots of different pieces. So I'm using in this to put them all back together again. And I'm going to use this case insensitively. And that's because you might have noticed that I only used uppercase E and uppercase J, but the APL allows you to use uppercase or lowercase. So this is just going to be case insensitive. And we do that on each of them. Go. So now we can have an order. So now we can have order on the names. And that means we can now sort. So now we have a supernatural sort, which is defined just like we had before, but instead of using grade, we're using this new order. And let's try it. Yeah, I can't really see what's going on. If you put them vertically, now you can see it. 1000 comes first, then my followed by nothing, then my followed by negative 0.01, then 1. This is 1e, okay? And this is 2, and so on. Notice that 10j negative 3 comes before 10j, even though nothing comes before something, but that's because we're looking at this as an entire number. And remember that we have this field where if we have negative imaginary part comes before the plain real number. So before that's what it comes for here. So that works. Anybody understood what was going on? Yeah, yeah, getting there, pushing the limits. One more.
Well, I don't know.
How are we on time?
Well, I mean, I'm quite flexible. I don't mind.
As you want. If it's interesting, we can keep going. Otherwise, I can easily round this off. There's just more examples and then summary, and I'm done. So whatever you want.
Well, we've got Stephen Taylor for 10-15-minute presentations, and then there's polyfillers. You and I don't mind. I mean, it's I'm happy that this is also.
Okay. Fine. One more example. Let's do something new. We can start defining this already. Getting exercise and typing this one. Okay.
You didn't get to do it with the swap?
No, and they didn't ask me about this first. I would have done it with a swap. You're right. Well, he's saying that I don't like parentheses. But notice that this is an idiom. But this is not an idiom. So yeah, doesn't really matter. I would write it like this instead. It's all the same thing. Okay. Okay, here is a phone book. Right, so last names, first names, telephone numbers. Those are the real numbers. Don't call us.
Sorry, Adám, to interrupt.
Yeah.
Ray was asking if different formats for the same number would be sorted or treated as equals, such as 10 equal versus 1
Yes.
equal.
With the natural ordering that we defined before, yes, it would, because we are converting them to number. Again, as I said in the webinar, you can always this is a fuzzy kind of science. It's something that's supposed to make sense to humans. A solution to that would be to, instead of replacing characters that represent the number with the number itself, you could prepend that number. So so that you end up, instead of having to compare 100 with 100, you would compare 100 followed by 1E2 to 100 followed by 100. Well, 1E2 is a character and 100 is that means that as a tiebreaker, when the first element is the same, you would use the original character data. Then you could get an absolute ordering. But I don't think anybody's expecting a natural sort ordering to be consistent, to be absolute. But yeah, sure, you could do it. It's not difficult. It'll be the next time I do this presentation, we'll do one more level of that.
But right now it's just stable, right? So it depends on the input.
It depends. Yeah, yes, it's stable. I even saw, when looking into all these things, I even found programming languages that when they had multiple elements, so not for sorting where you can't really tell difference, I think, but grading, multiple elements that compared the same, it would randomize the order of the input. Look at that. Sure, because then they can say there is no defined ordering, right? Isn't that just great? Yeah, look at that. Yeah. Hey, listen, I told you there are a lot of crazy solutions out there. I really looked into a lot of programming languages, and this is definitely the first time. I think it's like breaking new ground in mathematics or something like that. We're the first who have succeeded in taking an entire array model and making a sensible sorting order out of it. It just hasn't happened before in history. So it's not just fooling around. We're doing at the office. Doing raw research too. Okay, so let's go on with our phone book. So of course, by now you're not surprised that we can sort the phone book, right? But let's keep it sorted. Oops. Okay, now we have a sorted phone book. Here's an interesting one. Here's a new record. I want to insert this in our database, in our phone book. So one thing you could do, of course, is you could just append it to the end and then resort. But if you had a trillion entry database, that might not be the best idea every time you want to insert a new record in there. That might be a little bit expensive. So what we can do instead is we can take the phone book and we can ask APL with index interval index, where does it fit in? So it says it fits into the second interval. So this is the 0th, comes before the first entry. So first and the second, right? K comes between F and R. That's where it fits in. And so we can insert it like this. We can take the first two records and then insert the new one, and then insert the rest of the records. So now we didn't resort, but we still have it in sorted order. Inserted the new one in there. And we can even do it a little bit more elegantly by making it into a train. I don't know how many of you like doing tacit programming. Anybody who uses tacit programming? Trying? No? Okay, some of you don't know what it is. Okay, so tacit programming means we don't mention the arguments explicitly. There's no alpha, there's no omega, but we have a there's a function inside. So it means we're just saying the 2 and the PB, and they become arguments to take and to drop, and then we just insert this inside because it's going to give it the same thing. And then we can define this as a new function which inserts. So first we find the index, and then we insert it into the argument here. So now we can do into, new into the phone book. Works like this. What happens if we wanted to do multiple new entries? It wouldn't work. You can't take on different levels at the same level. So here's a cool trick that I got from Nick Nikolov, who gets it from K actually, and that is to use reduction as a means of repetition. So we have a power operator, but really reduction, yeah, somebody's nodding. Really, reduction is also something where you're doing something over and over again on every level. So we can do that in a pretty cool fashion. You'll see. So here we have another one. Okay, so now we have the new one, and the second new one, and the phone book. And now we can do an into reduction on this vector of new elements. And yeah, somebody's smiling over there. There you go. What happened? Well, remember what that reduction inserts this in between the elements, and we go from right to left. So this is really new 2 into the phone book, and that gives us a new phone book with this inserted element. And then this is the new phone book on the right, and then we have new 1 into the new phone book, and that inserts the second element again. And then we have to disclose because APL reductions reduce the rank. There you go. I think that's pretty neat. That's oh yeah. Sure. But yeah, but it's so much fun. Exactly. Yes, that's true. Okay, last example. Just a short one. Here's a spreadsheet, and I'm going to take the data out of here. Notice how nicely the Americans format their dates. Becomes very ambiguous. What is this? But APL can unambiguate disambiguate that for us. So I'm going to import this spreadsheet. For that, I'm going to create a new clipboard object. So I copied it to the clipboard from inside APL. Should have said that. Ooh. And it's just a temporary clipboard object, just long enough that I can manage to get the array value out. And oh, it's JD's magic here. So it converted these American dates to Quartillas format under the covers. I think that's pretty neat. And now you can see also from our box display that here we have numeric scalars. We have, well, I call it a ref, but it's a quad null scalar, and we have numeric vector, and there's a character vector. So it's lots of good stuff, mixed data in here. And of course, as I promised, it just works. You just sort it. So remember the rules. Null comes before everything. So that's, we go by the first element, the first column here. So null comes before a numeric vector. And for those that have the same value in here, we go by the next one over here. And of course, we can use all our old techniques. So we can do grading by some other ordering of our spreadsheet. So you're grading by first column 1 and column 3. So this is the dates, and then we skip the names over here. So again, you can see these are the same date, and null comes before numbers, and these two are the same date. So you can see that numbers come before characters, as we have defined that it should be. Right. So just to round this off, we mentioned a couple of times the many hundreds of emails. The initial idea for total array ordering was with Arthur Whitney, and K has something like that, although I disagree with the actual order, but the idea came from there. And then Roger Huey implemented that in J, a total ordering. We couldn't just adopt the total array ordering from J into APL because it very much depends on exactly how arrays work, and APL arrays are not the same as J arrays. So we had to come up with our own system. And there's the problem of J's ordering not being completely total either. And then much later, John Scholes wrote a model for this that you can still find in Defense, inspired by what was done in J. And that was our initial base as we started working on this. And then Roger started implementing based on the model in Defense. And then he sent out these experimental interpreters to us to play with, and I tried it out, and I found that it gave me results that was not what I expected. And here we are, 400 emails later from these 5 people.
Very good. We like.
So that's what you're getting in 17. Grade and sort, most arrays at least. Super fast if you use this idiom, or any of the other sorting, or other sorting idioms you can use as well for grade up, grade down, and principal index.
Great. Thank you.